So I'm going to, instead of skipping directly to the standard model, I'm going to say a couple of things about the intervening chapters, but not a great deal. And in particular, for chapter 23, I'm just going to go through in a little bit of... Where's the candy? I didn't bring the candy. I feel I carried it out here. Did I leave it?
Or it only shows up on camera. So I have to scour the way on camera.
Yeah, look for. Oh yeah, look off the camera. Where's the candy thief?
Sorry. Have to pay the TA.
Thank you.
Okay, so I want to go through one calculation of the running coupling constant in a little bit of detail, and that way you'll have that, you'll see that, I think, clearly. And then I'm going to go and do something about. There are many places to sit, whatever you want.
Sorry.
Then I'm going to do something about unitarity. And so let me see if we can get on with that. So let's see, maybe I'll use this other board a little bit. So what we've got, if we think in the conventional terms with counter terms, we've got the photon propagator like that. And if one is doing, one puts this in the T channel, for example, remember that then P squared is negative and one is computing corrections to Coulomb scattering, say. And what we found was E squared over P squared and 1 plus E squared over 2 pi squared. And you remember that we could say that, well, we can't really compute this from first principles because we don't know microscopic physics, but we can compute the derivative and integrate. And so what we'll get is effectively dx x 1 minus x log p squared x 1 minus x minus m squared over some p0 squared x 1 minus x minus m squared. So that's basically our expression here, and it actually is useful to think of p squared as negative in this case, because then we avoid an infrared singularity, because x1 minus x can get arbitrarily small, and that can shrink p0 down to m squared if it's positive. What we can say is that v tilde at some scale p0, well, obviously, at scale p0 squared, v of p0 squared is just e squared over p0 squared, because this logarithm then is log of 1, which is 0, and so the correction vanishes. So we can say, in fact, this is actually e squared at p0 squared divided by p0 squared. That's another way of thinking about it. Okay. Now, then E squared at P, V, the potential at P squared is going to be given by this more complicated formula. And what we know is that we don't want the potential, we don't want the potential at P squared to depend really upon p0 squared. In other words, it must be that E of p0 squared varies in such a way as to keep this whole thing independent of p0 squared. In other words, if you change the point, this I guess you can call it a subtraction point. If you change this point, you want E to compensate that change. And so what we're going to say is then that 0 equals, and for some reason people tend to write it this way. I don't know. I mean, this is going to play absolutely no role, okay, except to make things more complicated than they need to be. V tilde of p squared, this should vanish. Now, what is that? Well, it's cos p0 squared. And now, I was differentiating this afternoon, and I kept getting myself confused, because you differentiate this guy, and then you have to multiply that by these two terms, and then you keep this and you differentiate this guy with respect to p0 squared. So in other words, this is basically p0 squared, like that. That's the way we're thinking of it. And then finally, you keep all these guys constant and you differentiate the integral with respect to p0 squared. Okay, well, if you do that, what you get is 1 over p squared dE squared dp0 squared. That's the very first, that's just differentiating 1 times this. Then you can differentiate this times the integral, and that gives you 1 over p squared dE squared dp0 squared E squared over 2 pi squared. I'll just write it as the integral, because otherwise we're going to have too much notation. And then you can differentiate this guy, keeping this constant, and altogether that is E squared over 2 pi squared p squared dE squared dp0 squared, and then I'll just write this as an integral sign. And then finally we've got this, and experience shows that when you differentiate a log, you take advantage of the simple properties of log first and flip this p0 part into the numerator, overall minus sign. Derivative log x, 1 over x. Goes back into the denominator. Then you differentiate with respect to that, and you get 2p0x, 1 minus x. So doing that, what we get is minus e to the 4th over 2 pi squared p squared integral 0 to 1 dx x squared 1 minus x squared p0 squared x 1 minus x minus m squared. And I'm now just a little worried that there doesn't seem to be the 2 that I was missing.
You're missing a 2p.
Oh, I differentiate with respect to p0 squared,
Okay.
so duh. Well. Okay, so that's basically the expression. Now, let's simplify this a little bit. Well, first of all, we can get rid of this stupid p0 squared out in front, which was ridiculous. And then dE squared is E dE, obviously. And so what we've got is 2E, or rather dE squared is 2E dE. So we have dE dP0 squared plus 2E over P squared dE dP0 squared e squared over 2 pi squared integral 0 to 1 plus e cubed over pi squared p squared dE dp0 squared integral 0 to 1, and then finally minus e to the 4th over 2 pi squared p squared integral 0 to 1 dx x squared 1 minus x squared over p0 squared x 1 minus x minus m squared. Okay, so that's what we get as this all equals 0. So, by the way, when I was, I guess, a second-year graduate student, one of the best lecturers, Sidney Coleman, had finished a certain analysis, and he said, and it's all because we had an equation of the form something equals 0. A friend of mine said, but Professor Coleman, every equation is of the form something.
Yes.
That was one of the very few times that Coleman was ever caught out. Okay, if we rewrite this a little bit, we get dE dp0 squared, and notice that there's another spectator here, p squared 1 over p squared 1 over p squared 1 over p squared 1 over p squared. In fact, that may be the reason why. Well, but p and p0 are two different things. So if we multiply through by p squared, what we get is dE dp0 squared 2e plus e cubed over pi squared, the integral, plus e cubed over pi squared, the integral. And all of this is e to the 4th over 2 pi squared. And this is actually integral prime, I'll say, because after all, the first integrals were just this integral, and the second integral is this. So that's what I'm calling integral prime. All right. Now, if we look at this, we say this is e cubed. So why don't we say we're going to forget these things unless we're doing a higher order calculation? So I don't care. All right, so what we've got left is 2e dE dp0 squared is equal to e to the 4th over 2 pi squared 1 over p0 squared integral 0 to 1 dx. And I've pulled this p0 squared out, and what we have left is x squared over 1 minus x squared over x 1 minus x minus m squared. And, oops, well, it's actually m squared over p0 squared. So now, if we're talking positive p0 squared, we're just going to imagine that p0 squared, we're going to go to high energy so we can ignore this term. Or equivalently, we're talking about negative, we're going to let p0 squared go to minus infinity. So in other words, we're doing this process at very high energy. In that case, there's no infrared singularity. So we're going to forget this. And then that means that this thing is actually, after we cancel things, it's dE dp0 squared is then equal to, canceling the 2e and everything, it's e cubed over 4 pi squared, 1 over p0 squared, and now it's an integral 0 to 1 dx. And neglecting that, it's just x 1 minus x. And now this is, even in an age of Mathematica, I have enough residual calculus ability to do this integral. The integral of x is a half, the integral of x squared is a third, and so a half minus a third is a sixth. And so altogether this is e cubed over 24 pi squared 1 over p0 squared. Okay, so this should work at high energies, especially for negative p0 squared.
Why were we able to drop our e cubed terms, but we're keeping the e fourth term on the right of the equation?
Huh.
Is there some
Very,
relation
all right, let's,
from
let's,
E
let's,
cubed
let's,
to something else?
it's because this, we've already got the 2e term.
Yeah.
So it's that this is just a small correction to that.
Okay.
But I think that's a very good question.
Our integrals, the non-prime integrals, do have p's. And
Here, let me
maybe
give
it's-
you the good catch.
Maybe it's some relationship between e and p, or is it just, I don't know. Like what's,
All right,
what
let's just,
statement are we making when we drop the e cubed terms?
We don't care.
Other than
all right, let's suppose we kept these terms, and they're not all, let's see, it's the integral of 0, it's
this first.
it's this one over here. Well, let's drop m squared first of all. If we drop m squared, this is just log p squared over p0 squared. Oh, then of course you can do the integral and you get a sixth. So you'd have a log, so the extra correction would be 1 plus e squared over 2 pi squared 1/6 log of p squared over p0 squared. All right, now, let's just think about that for a minute. We were doing d by dp0 squared, and then I think set p squared equal to p0 squared, and this thing is 0. Okay. So that may be the correct answer to your question. I was following Schwartz, and he said he didn't care. But I think that's the better. In any event, what we get is this equation here, and that's a first-order differential equation. Now, of course, whenever you encounter a differential equation, you feel a little bit queasy. Because they can do things, differential equations tend to do things that are unexpected. And this one does too, actually. But anyway, what we do is we see this is dE, it's a first order differential equation. So this, when you have a first order differential equation, there's no question that there's a problem. You can always integrate it. So what you get is dE over E cubed is 1 over 24 pi squared dp0 squared over p0 squared. So in other words, the first step is you put the variables on opposite sides of the equation and you do both integrals. So this gives you minus a half 1 over e squared and now we're going to be integrating. So here we're all at p0 squared, which is why that term vanished. Now we're going to integrate from p0 squared to p squared. And so this is going to be 1 over e squared at p squared minus 1 over e squared at p0 squared. That's the left-hand side. And the right-hand side is 1 over 24 pi squared, and we get back the log. It's log p squared over p0 squared. So that's our expression. And now what you do is you isolate this and put everything else on the other side, and you get 1 over e squared at p squared is equal to 1 over e squared at p0 squared minus 1 over 12. Where's the 12 come from? Well, you multiply through by the 2 that was sitting over here. 12 pi squared log p squared over p0 squared. Now you just turn the equation upside down and you get e squared of p squared is equal to 1 over e squared of p0 squared minus 1 over 12 pi squared log p squared over p0 squared. And this looks perfectly awful until you realize where you can multiply top and bottom by e squared of p0 squared. And then you get e squared of p0 squared divided by 1 minus e squared of p0 squared over 12 pi squared log p squared over p0 squared. Okay. And so that's our e squared of p squared. It's equal to that. Right? Somehow when I do the erasing, it doesn't always. So e squared of p squared then is equal to this. So this is said to be the running coupling constant. And I used to make fun of that term, but I think it's actually appropriate because the idea is that in the vicinity of p squared, this thing is constant. After all, it just varies as 1 over a log. And e squared over 4 pi squared is 1 over 137. So this is 1 over something like 400. 1 over 400 times a log. And logs, you know, are so sluggish. They're the sleepiest of functions. And so consequently, this thing is more or less a constant, a coupling constant in the vicinity of p squared. And you can think of it as the effective coupling constant at momentum p squared. And now, what you see here is that the thing rises because as this becomes goes from 0 to something positive, this thing starts subtracting from 1, so you get a bigger value. And in fact, as you go from really low energies, where e squared over p squared, let us say e squared of 0 over 4 pi squared is 1 over 137, e squared at, let us say, the mass of the z, essentially, squared over 4 pi squared is something like 1 over 128. So it's changed enough to make a difference, but on the other hand, because the logarithm is so sleepy, it hasn't changed very much. On the other hand, when I said that differential equations do unexpected things, you see there is an unexpected thing, namely when log of p squared gets big enough, of the log of the ratios of the squared momenta becomes big enough, becomes equal to 12 pi squared over e squared of p0 squared, then you get infinity, and that's called the Landau pole. And so that's something that's unexpected. Now, maybe I should say a little more about this somewhat extemporaneously. What we've got here, let's plot then p squared this way, or minus p squared, whatever. Anyway, plotting the energy that way, what we've seen is that this thing grows from 1 over 137 to something like 1 over 128 at something like 100 GeV, well, it's 10 to the 4th GeV squared. If we're, because the mass of the Z is 100 GeV roughly. And on the other hand, the strong interaction coupling constant is really high, and it's coming down. And then what happens here is that there's also a weak coupling, and I should know how this varies, but I don't quite remember how it varies before and after. So let me just say it's, well, no, it's not doing. All right, I should have looked this up before doing this, winging this. But the point is that these guys, as you go to very, very high energies, what happens is, let's see, I'm going to have to get this to go down more, because these guys basically join, and you have unification of the electroweak. And then this thing is going down very slowly, this one is going down faster, and this is not the greatest plot, okay? But so this is, so to speak, E squared in quotes. The idea is that maybe they meet at some very, very high energy, and it's 10 to the 16th GeV squared, so it's really 10 to the 32 GeV squared. And they don't really meet, but if you put in supersymmetry, you can get them to meet. But of course, what's sort of artificial about this is that the way you get them to meet with supersymmetry is you say, okay, we've got the standard model, we make it supersymmetric in the right way. We then assume nothing happens, that that's the whole story, and as you go up in energy, there are no new particles, no new anything. There's no dark matter interacting at all with us. And so then you get them to meet. But of course, you know, who knows what's lurking there at higher energies. Well, I should say one more thing. You notice that this one goes up, and of course, once it becomes unified in here, it starts going down again. So either it's, I should have looked this up, either it goes down again, or it just sort of jerks here and goes up and meets. It may be that that's what we've got. It may still be going. I just don't remember how that works out. But the thing I do want to stress is that this is for SU3 of color. And what was discovered back in the 70s was, and this was by Coleman, one of the students, Politzer, I think, and also by, I think it was Wilczek at Princeton. And they both realized this. Namely, if you do this running coupling constant analysis, it's exactly the same, but you're doing it in SU3 instead of U1, which we'll be getting to maybe by the end of the hour. What you've got is you've got other terms. So you would have a gluon going along, and yeah, it can have a quark loop, but it can do something else. You can have a gluon go along, turn into two gluons, and go along. And you can also have a gluon go along, turn into three gluons. And you notice that this is a fermion loop, and you know, fermion loops have minus signs. These are boson loops, you don't have a minus sign. So these are basically opposite signs. And if there are if there are enough colors and few enough fermions, then this dominates. And so instead of having 1 minus, you get a 1 plus. And so that means that moreover, the coupling constant is stronger. And so that means that you get a weakening of the effective coupling constant as the energy goes up. for SU3, and for that matter for SU2. And the fact that it goes down eventually, that's called asymptotic freedom. And I imagine that was Sidney Coleman's phrase. He had a marvelous verbal facility. Up here, the fact that the thing gets so strong that it's able to confine quarks and gluons, this was called infrared slavery. I imagine that was Coleman also. I don't really remember who did what in the naming of these things. Okay, so that's enough of that. And let me invite questions because I'm about to switch to unitarity, implications of unitarity.
Okay, according to that expression, after this point, after the unified point, they are going to separate, right? I mean, the three lines are going to separate after this 10 to 16.
Oh, you're saying what would happen after here?
Right.
Oh, the idea, yeah, great point. Brilliant. What actually people think, the people who love this diagram think, is that up here you have just one coupling constant, which continues to run, and this is called a grandly unified group. In other words, the group here was SU3, the group here is SU2 left, the group here is U1, and when you get out here you have SU5, which Georgia and Glashow proposed in the mid-70s, or SO10, which Witten proposed, maybe probably others, I don't know, and all sorts of other possibilities. But you see, the gap between here and there is so huge, and God knows what else happens, and we know most of matter is dark. It seems to me very premature to be talking about this. And then, of course, the people who are all strung out have a different approach, although they don't. No, wait, I went to a string conference in Seoul almost by accident. I just happened to be in Seoul and the conference was there. And the atmosphere of the conference was very different from the atmosphere of a normal physics conference. It was closer to a poetry conference. It was in between a poetry conference and a physics conference. But anyway, I owe you candy. And I don't mean to dump on string theory. It could be right, you know. And there is one thing about it that's really nice, namely that... Oh, shit! Sorry. One nice thing about string theory is that the fundamental objects are extended in space. And if they're strings, they're extended only in one dimension, and that seems a little restrictive. So maybe the right theory is blob theory. All right, now we're going to go to unitarity. So applications of unitarity. Well, what we've got is a time revolution operator e to the minus I to h, let's see, t on psi of 0, and this thing is, it's actually, I've told you many times that this is kind of a fake, but never mind. It's true, and in others, it's effective. Okay, so here we've got from time, we can call that S. So S is sort of the limit of this as you go to large times, and there's a whole story there that we're going to skip. Now, what you expect is that, well, obviously that's a unitary operator. So S is a unitary operator, S being this in some sense. And we're going to write S as 1 plus IT. T is called the T matrix. And so the adjoint equation, the unitarity, this is called unitarity. This means that that's a unitary operator because H is summation. So if you write that out, 1 minus I T dagger, that's S dagger. 1 minus I T dagger, 1 plus I T equals 1. You cancel the 1 from both sides. What you get is I T minus T dagger plus T dagger T equals 0. And so you get I T minus T dagger is T dagger T. And, you know, this is one of those relations that's absolutely true as opposed to all the stuff when we're talking about, you know, if we're talking about quantum field theory, well, here's an action. Is it the true action? Are the particles supposed to be treated as point particles, or are they strings or blobs? So in other words, in most things you write down in physics, you don't really know, you don't really think they're absolutely true, it's just that they're sort of a model. This, on the other hand, is absolutely true. I mean, it's just mathematics. And taking matrix elements with a final state, I, T dagger minus T, initial state, well, of course, this is I, F, T dagger I, minus I, F, Ti, and now you know that the definition of a Hermitian operator is such that this is actually I, T, F complex conjugate minus I, F, Ti. On the other hand, back in the early chapters of Schwartz's book, he related the T matrix to scattering amplitudes, and what we have here then is I 2 pi to the 4th delta 4 for pi minus pf, and then we have this one is m star, f goes to I minus m, I goes to f. So that's the left hand, that's a matrix element on the left hand side of the unitarity equation. The right hand side is an integral of, well, it's f, T dagger, and then we put in an arbitrary state, x, initial state, and then we have d pi x ellipse, and we're, of course, summing over a complete set of states here, x. So this is the identity operator. And now, if you repeat this connection between the matrix, the T matrix elements and the scattering amplitudes, what you see is that this is sum over x, 2 pi to the 4th, delta of pf minus px, 2 pi to the 4th, delta pi minus px, and I think I better integrate somewhere here. Integrate d pi x, that's this thing. And that's whatever this must be in order to make this a complete set of states. Okay, you might have kinematic factors according to how the states are normalized. So I shouldn't have said ellipse. It might be something a little bit different depending on the normalization. Anyway, this is d pi x, m star, f goes to x, times m, I goes to x. Was there a question back there?
I was just wondering what happened to T.
Yeah, you dropped it.
It should be between the X and the I.
This one?
One more down. 2 more down.
That became that.
And then, when you put in the general states of X,
Right. Oh, shit. It was right. Yeah.
okay, I just,
Yes. All right, you're entitled to 2 candies. Good thing this is on YouTube rather than something the FCC has control over. Already thrown off the air. All right, so this is our expression, so this one is that. Okay, so what we've got then, when you do this integration, of course, these delta functions, the product of the delta functions gives you, in particular, an overall delta function. In other words, if px is equal to pi and also equal to pf, then pi has to be pf. So that gives this. And so what we get then finally is m of I goes to f minus m star of f goes to I. I sum on x integral d pi over the intermediate states 2 pi to the 4th delta pi goes to px m I goes to x m star f goes to x. So this is one way. This is called the optical theorem. This is one of many, many, many forms of the optical theorem. Now, what? As I said, this is a pretty remarkable relation. Let me just get down to this part here. You see, this says that something linear in T, the imaginary part, in a sense, of T, is the squared modulus of T. So that's a very interesting relationship. So let us say that I and F are the same. We'll call it A. Then this is A goes to A, M of A goes to A minus M star of A goes to A. Well, that's just the imaginary part, or twice the imaginary part, or 2I times the imaginary part of M. A goes to A. And on the right-hand side, things also simplify a little bit. It's, well, there's an I, so we're going to have to cancel that I at some point. Integral d phase space 2 pi to the 4th delta 4th pa goes to px, and now I and f are the same, so this is just the absolute value of m a goes to x squared. So now this is all quite sensible, and in fact, if let's get rid of these stupid extra i's, or in fact, let's even move the 2. So what we've got is that the imaginary part of the process of A goes to A, so this is really the imaginary part of some forward scattering amplitude, if it's a scattering process, because these two are exactly the same. It's a half the integral over some phase space of the matrix element for A goes to anything, squared, summed over everything, or anything. And so that's a very tantalizing thing. And it's really one of the remarkable things. People got so excited about this back in the 60s, especially on the West Coast, that they combined this unitarity together with the fact that scattering amplitudes can be expressed as Fourier transforms of Green's functions and so on and so forth, that LSZ business. And when you look at it, you see, well, you've really got an analytic function of several complex variables. That's the way you can rewrite it as that, write it in that form. And then they thought, wow, we've got something involving analytic functions of several complex variables, and you know how special analytic functions are. And moreover, we've also got these exact nonlinear relationships. And so the thought was that people could really do some remarkable things. And this was prompted by some papers by Mandelstam, who did do some remarkable things, and some others. But they really went, I think, off the deep end and into the Pacific Ocean. Because, and the real progress in physics, and on the East Coast, there was a corresponding illusion. There, some people at Princeton, Flynn, Jaffe, and their students thought, and Whiteman, I guess, thought that they could analyze quantum field theory mathematically and constructively and really figure everything out from the point of view of real mathematics. And meanwhile, the actual progress was made by Weinberg, Salam, and Georgia, not Georgia, Clasha. And what they were doing was they were using non-abelian gauge theory and saying that, well, they were constructing the standard model. And so the people on the East and West Coast, most of them, the whole fashion was to throw out quantum field theory. Weinberg and Glasgow and Salam were saving it. And of course also the Dutch group, Veltman and at Hoft, were showing well, they were inventing dimensional regularization and showing that this was a way of renormalizing the Higgs mechanism. And of course Peter Higgs invented the Higgs mechanism in '64. So this is all happening basically in the 60s, the sensible things by, as I said, Higgs at Hoft, Glasgow, Weinberg, Salam, and then all the attention was devoted instead to functions of many complex variables, unitarity, and constructive quantum field theory. So you never know what's what, because now the contract's being written against me. Okay, so that's a nice form of the optical theorem, and in particular, if A is a one-particle state. Okay, so what is it? What can you say? Well, first of all, what is the decay rate? The decay rate is A goes to anything, basically. And this, I think we saw this at some point. Anyway, it's 1 over 2 mass A d pi x, the invariant phase space for whatever the final state x is, and then 2 pi to the 4 delta 4 pa minus px m of A goes to x absolute value squared. All right, so that's the decay rate. And so what do we have? On the right-hand side, we've got essentially the decay rate. On the left-hand side, we've got an imaginary part of this amplitude, A goes to A. So the imaginary part of M of A goes to A, so this is just kind of like the propagator, isn't it? Or the imaginary part of the propagator is equal to M sub A, sum on X, decay rate of A goes to X, and so this is just MA times the total decay rate, or MA over the lifetime of particle A. All right, now let's look at the case of two particles. So if A is two particles, then the cross-section, sigma, if A goes to anything, and we're here center of mass and so forth, E center of mass, the momentum in the initial state, integral phase space of the final of X, final state particles, to pi to the fourth, delta fourth, PA minus PX. All right, hold on. Absolute value of M, A goes to X squared. Okay, so that's the total cross-section of A goes to anything, A being two particles. 2 goes to anything. All right. So that's that. What does the optical theorem say? The optical theorem says that the imaginary part of M of A goes to A, which is to say the forward scattering amplitude, that this is equal to 2 E center of mass pi, the initial momentum, 3 momentum, magnitude of the 3 momentum in the center of mass frame. And now sum over all final states, the cross-section A goes to anything. So, and this is then this is the total cross-section, A goes to anything. In fact, it's summed over everything. So this can be rewritten as 2 energy center of mass, momentum, 3 momentum, magnitude of the 3 momentum, sigma total of A goes to anything. In other words, the sum over all the possible final states. So that's another very interesting relation. All of these optical relations are both interesting and exact. And so they're exact and they're nonlinear, and that's, yeah, I mean, that's why the people on the West Coast got so caught up with this. It's, you know, they might have been right. Nature has been good. Okay, now I want to go to the case of partial waves. And in particular, so partial waves. And this is something you study in quantum mechanics class. And so we're going to be talking about 2 particles, those are 2 particles, elastic scattering. Elastic, of course, means the energy of the final state is the same as the energy. Kinetic energy in the final state is the same as kinetic energy in the initial state. And in fact, we're thinking of A plus B goes to A plus B. So we also have the same particles in the final state. All right. So what do we have as, what do we know? Well, first, and I'm going to write this as AB goes to AB, by which I mean this. So the sigma total, what is it? Well, this is, it turns out, we found months ago, this is 1 over 32 pi, E squared, E center of mass squared, integral D cosine theta. The amplitude is a function of theta squared. And if you want to know where did this come from, this came from, you integrate equation 5.32 over the azimuthal angle phi. All right. Now, m of theta, well, any function of theta, of course, can be written in terms of Legendre polynomials. Chapter 8 or so in my book. All right, so m of theta, or maybe 9, I don't remember. Anyway, we can write it as 16 pi, just an overall normalization. Coefficients aj, which can be complex, j equals 0 to infinity, 2j plus 1 pj of cosine theta. So that's just a general mathematical result to Legendre. All right. Now, these Legendre polynomials are orthogonal, and the best thing to do is to replace this with x. Cosine theta has to be between -1 and 1, and so, and d cosine theta from 0 to pi is dx from -1 to 1. And so the orthogonality in a more sensible notation is pj of x, pk of x, integrated dx, 2 over 2j plus 1 delta j plus 1. So that's the orthogonality of the Legendre polynomials. By the way, you can think of these Legendre polynomials as, if you take the monomials, 1x, x squared, x cubed, x fourth, and so forth, and then you make them orthonormal like this, and you also include a normalization condition, and I think the normalization condition is pj, is it of 0 is 1, or pj of -1, or pj of 1 is 1. Anyway, there's some normalization condition together with the orthogonality or orthonormality gives you the actual Legendre polynomials. Okay, let's take this expansion and put it in here. And here's the total elastic scattering cross-section. So it's not total cross-section, total elastic. So sigma, maybe we should call it total written this way. AB goes to AB. And this then is 1 over 32 e squared integral dx, x being cosine theta. And now this is 16 pi sum aj 2j plus 1 pj of x star 16 pi sum on k ak 2k plus 1 pk of x there. The star is not because we need a star in the orthonormality. These guys are real because these are real polynomials in a real variable x. Okay, you use the orthonormality, and what you get is that this total cross-section is then 16 pi over e squared center of mass, sum j equals 0 to infinity, 2j plus 1, absolute value of aj squared. And of course, you get the absolute value because you have aj star there, ak here, you get j for the k, so that gives you aj absolute value squared. You have two factors of 2j plus 1, but the orthogonality relations gives you a 1 over 2j plus 1. So altogether, that's what you've got. So what does this say when you get back to the optical theorem? When you apply the optical theorem, what it says is that the imaginary part of the amplitude AB goes to AB, and if we go to theta equal to 0, This is forward, in other words. So remember, we're setting initial state. What we do to get the nice results, we set initial state equal to final state. So not only is it elastic, but it's forward scattering. And so this is 2e center of mass, initial 3 momentum, sum on x, sigma total, and now this really is, this is tot, or it's total, as opposed to total. And so that's our that's the optical theorem. And now, of course, this optical theorem, this sum over all final states is, of course, greater than or equal to E center of mass momentum, any particular total cross-section of, for example, AB goes to AB. So this is, in the final state, theta isn't necessarily 0, it's anything, and but it's elastic. Okay. So this is a weaker version of that. On the other hand, we can take this amplitude here, we've already expressed it as in terms of these Legendre polynomials, and so what we get is the sum 2j plus 1, the imaginary part of aj. In other words, we're taking, we're on the left-hand side we have theta equal to 0, so these guys are all 1. I guess that's the condition I was thinking of. Pj of 0 is theta equal to 0. Pj of 1 is 1, so it's Pj of 1 equals 1. That's the normalization condition. You take the imaginary part of that, and apart from an overall factor, you get this, and then that's greater than or equal to 2 pi over E center of mass, and now sum j plus 1 aj squared. So in other words, you have to, well, there's total, but yeah, that is the, okay, so that's just this. So I'm just using that there, and anyway, just to, so this is the relation that we have, and it's got all these sums, but now you can say, well, this tells us something because this is aj squared. So suppose aj is, suppose, this means that this can't get too big, the aj, because it's less than the imaginary part. And this becomes clearer if we focus on a single partial wave. So let's look at a single partial wave. Then what we'll have is that this equation will tell us, especially, well, let's just look at a single aj. We have aj, this is the square, let aj equal x plus iy. So this is x squared plus y squared. And this, of course, is greater than or equal to absolute value of y. So the imaginary part is less than the total absolute value. And this gives us a bound on the partial waves. And if we go to the limit where E center of mass is much greater than MA and MB, then it turns out that P is a half E center of mass. That's what the initial momentum is. And so this thing is just 1. And if we're focused on a single partial wave, the 2j plus 1 cancels, and we have this equation. Imaginary part of aj equals absolute value of hj squared. Well, that just says that y is equal to x squared plus y squared. It says in particular the imaginary part is positive. And now, if we think about what that means x squared plus y squared minus y equals 0. This is an equation of the Coleman type. And so we can rewrite that as x squared plus y minus a half squared. And that gives us a plus a quarter. So we have to subtract a quarter, or putting it on the other side, we get a quarter. So this is the equation for a circle of radius a half about the point 0, 1/2. And for some reason this is called an Argand diagram. All right, so now this is something that we're going to return to when we're dealing with Yang-Mills theory later, because, and in fact, I think we can start basically almost immediately. I don't plan to do any more of the intermediate stuff. This says then that, well, when you have, let's review what we've got here. We've got that for the case of high energy, one partial wave, and you can imagine that there's only one partial wave involved in some process. Then this amplitude, which is x plus iy, well, xy is on this. In fact, it's just, these are all just things of radius a half. So the amplitude is just, the possible values of the amplitude are just the points on this circle. And so that means that the thing in particular is bounded. You can't have these partial wave amplitudes be too big. And so what it turns out, though, is that in some theories, if you go to high energies, you can see that the amplitudes will increase with energy. And so there's something then that is wrong if they're increasing. In other words, if you do a calculation and you find the amplitude increasing, then there are two possibilities. One is that you're just doing perturbation theory and you haven't included enough terms, and if you included all the terms, you'd see things weren't increasing. The other is that there's new physics that has to come in that you haven't yet included, and that physics will bring the amplitude down. One result was derived from this stuff. It was called the Froissart upper bound. Let's see, I don't know if Schwartz actually mentioned what that was explicitly. Let me see if I can. All right, let me give you the Froissart upper bound. This is something else, but it's from these same things. It's that the total cross section is bounded by something like log squared of E center of mass at high energies. Now this was, Froissart was rather mathematical, so let's say that would be rather a complicated thing to derive, so I'm not going to try to derive that. All right, as we speak, before ending the lecture, let me just say a couple of words about Yang-Mills theory, just so that you have very clearly in mind the basic idea. The basic idea is that for some reason nature really loves symmetry, and people don't agree on why that's true, but what seems to be going, but it is true. And one of the reasons, of course, is that our description should be such that it's independent of the conventions we use to write our description. And the way in which a theory becomes independent of the conventions that we use to describe it is if it's a tremendously symmetrical theory. And so, for example, when you do, in general relativity, what you have is you have a description of space-time in which the equations are invariant under general coordinate transformation, which is pretty amazing. X mu goes to x mu prime, arbitrary function of the 4 x mu's. And if you do that, all equations, everything cancels, and it's just everything, the same equation with primes everywhere. This has always confused the hell out of me, because then I never know what coordinate system are we talking about. What the hell is time? What the hell is space? In Yang-Mills theory, it's the way I like to think about it is that the labels we give to electron, muon, protons, spin up, spin down, all these other things, the theory has to be invariant under that. And the way in which it happens in Yang-Mills theory, this is the great advance of Yang and Mills, is that you say that psi I of x is some u, well, I'll write it as ij of x, psi j of x. So we have, where this is some unitary matrix, depending on space-time. You can have a different matrix at different points of space-time. And for practical purposes, we're not going to pay attention to upper and lower indices here. It's important for non-compact groups, but for compact groups typically isn't. And so we're going to start from that point next time, so I guess we can